Hello and good day. This is the presentation about Mohan's paper on the transaction management in the RSTAR distributed database management system. Our quick agenda for this presentation, I will discuss about the background and the motivation of the authors. Second is to present the contributions and the key points that was made. And lastly is how things are implemented in system RSTAR. So just to recap, a distributed database system is the combination of database systems and computer network technologies, where it forms an integrated collection of physically distributed, logically interrelated databases across sites in a computer network. In a distributed database system, actions of a transaction may occur at more than one site. Transactions permit multiple data manipulation and definition statements to constitute a single transaction. Conditional execution and ad hoc SQL statements are available to the application program, and the whole transaction need not be fully specified and made known to the system in advance. A distributed transaction commit protocol is required in order to ensure either that all the effects of the transaction persist or that none of the effects persist, despite intermittent site or communication link failures. In other words, a commit protocol is needed to guarantee the uniform commitment of distributed transaction executions. When we say uniformity, we usually refer to consistency. And to guarantee uniformity or consistency, certain facilities must exist in a distributed database system. First is that each action of a transaction can be undone if it is or needs to be aborted. This means that each process is able to provisionally perform the actions of a transaction. Second is each state changes are recorded or logged sequentially in a stable or non-volatile storage for recoverability. And since we are talking about multiple physical databases within a network, each database has to have a log for this purpose. Now, there are two ways on how logs can be written. So the first one is synchronous or force writes. This assures survivability of an action or transaction right at the end of transaction, since the forced log record and all preceding ones are immediately moved from the virtual memory to the persistent layer or stable storage. If in force writes, transactions are not allowed to continue execution until the logging is complete, asynchronous or writes allows this. The record gets written to virtual memory buffer storage, and it gets migrated to the stable storage either with a manual trigger or when a log page buffer fills up. However, this means that if the site crashes after the log write, since it is not yet moved to the stable storage, then the record may not be available for reading upon recovery. To ensure reliability on distributed database systems, we have what we call the Twophase commit protocol. And this specific protocol ensures the atomic commitment, or again, the atomicity and consistency of distributed transactions. It insists that all sites involved in the execution of a distributed transaction agree to commit the transaction before its effects are made permanent. And for a commit protocol, we have some desirable characteristics. First, again, is that it guarantees atomicity of transactions. It is able to forget outcome of commit processing after a short amount of time. It has minimal overhead in terms of log writes and message traffic. It is also optimized in terms of performance in the no failure case, and it should exploit completely or partially read-only transactions, and it maximizes the ability to perform unilateral aborts. Now, the challenge for the authors is that the discussions in the literature about commit protocols are usually vague, if there is any mention at all, about the correctness and performance of these protocols. So the idea here is that since distributed query processing algorithms are efficiently implemented as a tree of cooperating processes, multi-level hierarchical commit protocols are more natural than the conventional two-level protocols. Now let's see how the two-phase commit protocol works on a normal basis. So in a 2P commit protocol, the model of a distributed transaction execution is such that there is one process called the coordinator, in this case C, that is connected to the user application, and a set of other processes called the subordinates, in this case S1, S2, S3, and S4. When the user decides to commit a transaction, the coordinator, which receives a commit transaction command from the user, initiates the first phase of the commit protocol by sending prepare messages in parallel to the subordinates to determine whether they are willing to commit the transaction. Each subordinate that is willing to let the transaction be committed first force writes a prepare log record and then sends a yes vote to the coordinator and waits for the final decision from the coordinator. Each subordinate that wants to have the transaction aborted force writes an abort record and sends a no vote to the coordinator. Now the force write then voting is necessary for recovery. If a crash happens between voting and force writing, then the recovery process, which will be discussed later, will not know what is the planned activity for that process, which may result in the wrong action being taken at restart. Now let's consider that all subordinates submitted yes votes. The subordinates or the process is said to be in the prepared state if they sent a yes vote, and it cannot unilaterally commit or abort the transaction. If all the votes were yes votes, then the coordinator moves to the committing state by force writing a commit record and sending commit messages to all the subordinates. Each subordinate, after receiving a commit, moves to committing state, force writes a commit record, sends an acknowledgement or ACK message to the coordinator, and then commits the transaction and forgets it. The completion of the force writes takes the transaction to its commit point. Once this point is passed, the user can be told that the transaction has been committed. How about if there is at least one no vote, like the initial situation? Since a no vote acts like a veto, the subordinate knows that the transaction will definitely be aborted by the coordinator. Hence, the subordinate does not need to wait for a coordinator response before aborting the local effects of the transaction. Therefore, the subordinate aborts the transaction, releases its locks, and forgets it. Now, if the coordinator had received even one no vote, as our current situation, then it moves to the aborting state by force writing an abort record and sends aborts to only all the subordinates that are in the prepared state or have not responded to the prepare. Each subordinate, after receiving an abort, moves to the aborting state, force writes an abort record, sends an ACK to the coordinator, and then aborts the transaction and forgets it. The coordinator, after receiving ACKs from all the subordinates that were sent a message in the second phase, writes an end record and forgets the transaction. By requiring the subordinates to send ACKs or acknowledgement, the coordinator ensures that all subordinates are aware of the final outcome. By forcing their commit or abort records before sending the acknowledgement, the subordinates make sure that they will never be required, while recovering from a processor failure, to ask the coordinator about the final outcome after having acknowledged a commit or abort. This general principle adheres to transaction atomicity. If the subordinate still has to ask the coordinator about that piece of information, then it means that atomicity may not be guaranteed. Now, the log records at each site contain the type of the record, the identity of the process that writes the record, the name of the transaction, and the identity of the coordinator. The names of the exclusive locks held by the writer in the case of prepare records, and the identities of subordinates in the case of commit abort records written by the coordinator. This is a simple visualization that was prepared or presented in the literature by the authors. Now, how about when there are any site or communication link failures? Now, each active site has a recovery process. The recovery process processes all messages from recovery processes at other sites. It also handles all the transactions that were executing the commit protocol at the time of the last failure of the site. Now, as part of recovery from a crash, the recovery process at the recovery site reads the log on stable storage and accumulates in virtual storage the information relating to transactions that were executing the commit protocol at the time of the crash for the following purposes. One is to answer queries from other sites about transactions that had their coordinators at this site. And second is to send unsolicited information to other sites that had subordinates for transactions that had their coordinators at this site. Having the information in virtual storage allows remote site inquiries to be answered quickly, and hence there will be no need to consult the log on the stable storage to answer these queries. Now, how does it work? So when the recovery process finds that it is in the prepared state for a particular transaction, it periodically tries to contact the coordinator site to find out how the transaction should be resolved. When the coordinator site resolves a transaction and lets the site know the final outcome, the recovery process takes the steps outlined before a subordinate when it receives an abort or commit. So if the recovery process finds a transaction was executing at the time of the crash and that no commit protocol log record had been written, it aborts that transaction by undoing its actions, if any, using the undo log records, writing an abort record, and forgetting the transaction. The recovery process neither knows nor cares whether it is dealing with the subordinate or the coordinate of the transaction. If the recovery process finds a transaction in the committing, respectively aborting state, it periodically tries to send the commit or abort to all the subordinates that have not acknowledged and awaits their acknowledgements, or ACKs. Once received, or once all the ACKs are received, the recovery process writes the end record and forgets the transaction. In addition to the workload that the recovery process accumulates by reading the log during restart, it may be handed over some transactions during normal operation by local coordinator, and subordinate processes that notice some link or remote site failures during the commit protocol. And here we assume that all failed sites ultimately recover. If the coordinator process notices the failure of a subordinate while waiting for the latter to send its vote, then the former aborts the transaction by taking the previously outlined steps. If the failure occurs when the coordinator is waiting to get an ACK, meaning after the coordinator sends his commit or abort to subordinates, then the coordinator hands the transaction over to the recovery process. Now we have two further scenarios. So if the subordinate notices the failure of the coordinator before the former sent a yes vote and moved into the prepared state, then similarly to the first situation, the recovery process aborts the transaction, and this is what we call the unilateral abort feature. And on the other hand, if the failure occurs after the subordinate has moved into prepared state, similar to the second scenario, then the subordinate hands the transaction over to the recovery process. Now, when a recovery process receives an inquiry message from a prepared subordinate site, it looks at its information in virtual storage. If it has the information that says the transaction is in the aborting or committing state, then it sends the appropriate response. Now the question is, what if there's no information found in the virtual storage? The general answer is to abort the transaction, and the literature offers the procedure or detailed procedure on how it's being done. Now, there are issues with regards to this traditional two-phase commit protocol. The 2P is traditionally inadequate for transaction execution model with multi-level trees of processes. Each process communicates directly with only its immediate neighbors in the tree, that is, parent and children. And in fact, a process would not even know about the existence of its non-neighbor processes. So to address these issues, the authors introduced the concept of hierarchical two-phase commit protocol, where we have the root process that is connected to the user or application acts as the coordinator, and it only acts as a coordinator. The leaf processes acts only as subordinates, and the ones in between, the non-leaf and non-root processes, act as both coordinators and subordinates. So how does it work? First is that the root and the leaf processes act as if they are in a non-hierarchical two-phase protocol. Now, the non-root, non-leaf processes, after receiving a prepare message, propagates it to its subordinates, and only after receiving their votes does it send its combined vote to its coordinator. When we talk about combined vote, we usually talk about the vote of the entire subtree. Now, the subtree voting consists of the votes of the subordinates and the votes of the subtree's root process. So, similarly, if any vote is a no, then the subtree vote is a no. Otherwise, vote is yes. Now, a non-root, non-leaf process in the prepared state, on receiving an abort or commit, propagates it to its subordinates after force writing its commit record and sending the acknowledgement to its coordinator. With that idea of hierarchical two-phase commit protocol, the authors introduced two extensions of this two-phase commit protocol, which is the presumed abort and the presumed commit protocol. First, we will discuss about the presumed abort protocol and its motivation. So we know that it is safe for a coordinator to forget a transaction immediately after it makes a decision to abort it and to write an abort record. So this means that the abort record need not be forced both by the coordinator and each of the subordinates, and no acknowledgements need to be sent by the subordinates for aborts. Furthermore, the coordinator need not record the names of the subordinates in the abort record or write an end record after an abort record. Also, if the coordinator notices the failure of a subordinate while attempting to send an abort, the coordinator does not need to hand the transaction over to the recovery process. It will let the subordinate find out about the abort when the recovery process of the subordinate site sends an inquiry message. So with this, we will consider how to actually take advantage of completely or partially read-only transactions or read-only transactions. So how does it work for the completely read-only transactions? So just to set the definitions, a transaction is considered completely read-only if no process of the transaction performs any updates. So in part 1 of the procedure, we do not need to know before the transaction starts whether it is read-only or not. So if a leaf process receives a prepare message and it has not done any updates, then it sends a read vote, releases its locks, and then forgets the transaction. The subordinate in return writes no log records. So as far as it is concerned, it does not matter whether the transaction ultimately gets aborted or committed. So the subordinate, who is now known to the coordinator to be read-only, does not need to be sent a commit or abort by the coordinator. A non-root non-leaf sends a read vote only if its own vote and those of its subordinates are also read votes. Otherwise, as long as none of the latter is a no vote, it sends a yes vote. Now, the second part of this procedure is if the root process is read-only and it gets only read votes. In this case, the root process writes no log records for the transaction. On the other hand, if the root process or one of its subordinates votes yes and none of the others vote no, then the root process behaves as in the usual two-phase commit protocol. We note that it is sufficient for a non-leaf process to include in the commit record only the identities of those subordinates, if any, that voted yes. And those who voted yes are only those processes who will be in the prepared state, and hence only they will need to be sent commits. If a non-leaf process or one of its subordinates votes no, then the former behaves as described in the earlier section. So in summary, none of the processes write any log records, but each one of the non-leaf processes sends one message, which is prepare, to each subordinate, and each one of the non-root processes sends one message, which is a read vote. Now let's look at the partially read-only transactions. Again, by definition, a transaction is considered partially read-only if some processes of the transaction do not perform any updates to the database while the others do. So the first is the root sends two messages to each update subordinate. One is the prepare message and the other is the commit message. And it also sends one message to the read-only subordinate, which is the prepare message. Now, each one of the non-leaf, non-root processes, that is the root of an update subtree, sends two messages to each update subordinate, which is prepare and commit. It sends one message to other subordinates, which is prepare, and two messages to the coordinator, which is a yes vote and acknowledgement, or ACK. Now, each one of the non-leaf, non-root processes, that is the root of the read-only subtree, it behaves like completely read-only transaction following the presumed abort protocol. Each one of the non-leaf processes writes three records: prepare and commit, which are forced, and end record, which is not forced. It also writes two records if the non-leaf process has no update subordinates, which is a forced prepare and forced commit. Now, the read-only leaf process behaves just like the one in a completely read-only transaction following presumed abort, and an update leaf process behaves like a subordinate of a committing transaction in two-phase commit protocol. By making the above changes to hierarchical two-phase commit protocol, we have generated the entire presumed abort protocol. The name arises from the fact that in no information case, the transaction is presumed to have aborted, and hence the recovery process's response to an inquiry is an abort. Now let's look at the presumed commit protocol. So the question here is that could commits be made cheaper by eliminating acknowledgements for commits? Now, in order to require the aborts be acknowledged while commits need not be, and also that abort records be forced while commit records need not be by the subordinates, The consequences are that in the no information case, the recovery process responds with a commit when a subordinate inquires. So, considering this situation, when a root process sends prepares, one subordinate has gone into the prepared state, and before the root process is able to collect all the votes and make a decision, the root process crashes. So far, the root process would not have written any commit protocol log records, and when the crashed root process's site recovers, its recovery process will abort this transaction and forget it without informing anyone, since no information is available about the subordinates. When the recovery process of the prepared subordinate site then inquires the root process's site, the latter's recovery process would respond with a commit, causing an unacceptable inconsistency. So the solution here is the presumed commit protocol, where each coordinator records the names of its subordinates safely before any of the latter could get into the prepared state, and then when the coordinator site aborts on recovery from a crash that occurred after the sending of prepares, but the coordinator moved into the prepared state in the case of the non-root coordinators, the restart process will know who to inform and get acknowledgments about the abort. So how does each of the entities or process behaves? Okay, so a non-leaf process behaves similarly as in presumed abort, except that at the start of the first phase, before sending the prepares, it force writes a collecting record, which contains the names of all the subordinates and moves into the collecting state. It force writes only abort records, except in the case of the root process, which force writes commit records also. It requires acknowledgements only for aborts and not for commits. It writes an end record only after an abort record, if the abort is done after a collecting record is written, and not after a commit record. Now, only when in the aborting state will it hand over the transaction to the restart process. In the case of completely read-only transaction, it would not write any records at the end of the first phase in presumed abort, but in presumed commit, it would write a commit record and then forget the transaction. Now, how do the subordinates behave? Now, the subordinates behave as in presumed abort protocol, except now they force write only abort records and not commit records, and they acknowledge only aborts and not commits. On restart, if the recovery process finds for a particular transaction a collecting record and no other records following it, then it force writes an abort record, informs all the subordinates, gets AC case from them, writes the end record, and forgets the transaction. And in the no information case, the recovery process responds to an inquiry with a commit. So the name arises from the fact that in no information case, the transaction is presumed to have committed, and hence the response to an inquiry is a commit. Now let's look at the procedure for both completely read-only transaction and partially read-only transaction. So let's look at the completely read-only first. On the commits for completely read-only transactions, each one of the leaf processes writes two records. So forced collecting and not forced commit. And then it sends one message, which is prepare, to each subordinate. Furthermore, each one of the non-leaf, non-root processes sends one more message, which is a read vote. Now, the leaf processes write no log records, but each one of them sends one message, which is a read vote, to its coordinator. For partially read-only transactions, the root process writes two records, which is a forced collecting and forced commit, and sends two messages, which is prepare and commit, to each subordinate that sent a yes vote, and one message, which is prepare, to each one of the other subordinates. Each one of the non-leaf, non-root processes, that is the root of an update subtree, sends two messages, which is prepare and commit, to each subordinate that sends a yes vote, one message which is prepare to each one of the subordinates, one message which is a yes vote to its coordinator, and it writes three records, which is forced collecting, forced prepared, and not forced commit. Read-only leaf processes and processes that are roots of read-only subtrees, hence the entire read-only subtree, behaves just like the corresponding processes in a completely read-only transaction in presumed commit. Now, the update leaf process sends one message, which is a yes vote, and writes two records, which is a forced prepare and not forced commit. In the paper, they summarize the comparison of all the log writes and messages for the three protocols presented: the standard two-phase commit, the presumed abort, and presumed commit. Okay, we can see here the summary of their the number of records written, how many of them are forced, which ones are for the coordinator, now the number of messages sent, okay, and the number of messages sent to coordinator by a subordinate, and also the number of messages sent to each update subordinate. Now, it turns out that the presumed abort is better than the standard two-phase commit protocol, because it is obvious that the presumed abort performs better than presumed commit in the case of completely read-only transactions, because it saves the coordinator two log writes, including a force, and in the case of partially read-only transactions in which only the coordinator does any updates, saving the coordinator a force write. Now, the presumed abort and the presumed commit require the same number of messages to be sent. In the case of a transaction with only one update subordinate, PA and PC are equal in terms of log writes, but PA requires an extra message, which is the acknowledgement sent by the update subordinate. For transaction with more than one update subordinates, both PA and PC require the same number of records to be written, but PA will force n-1 times when presumed commit will not. These correspond to the forcing of the commit records by the subordinates, and in addition, presumed abort or PA will send n extra messages. Now, depending on the transaction mix that is expected to be run against a particular distributed database, the choice between presumed abort or presumed commit can be made. It should also be noted that the choice could be made on a transaction-by-transaction basis instead of a system-wide basis at the time of the start of the first phase by the root process. At the time of starting a transaction, the user could give a hint, but not a guarantee, that it is likely to be a read-only, in which case presumed abort could be chosen. Otherwise, presumed commit could be chosen. It should be pointed out that our commit protocols are blocking in that they require a prepared process that has noticed the failure of its coordinator to wait until it can re-establish communication with its coordinator site to determine the final outcome of the commit processing for that transaction. The authors have extended but not implemented presumed abort and presumed commit to reduce the probability of blocking by allowing a prepared process to encounter or that encounters a coordinator failure to ask its peers about the transaction outcome. The extensions require an additional phase in the protocols and result in more messages and or synchronous log writes even during normal times. Now, given that we have an efficient commit protocols, presumed abort and presumed commit, and the fact that remote updates are expected or postulated to be infrequent, the time spent executing the commit protocol is going to be small compared to the total time spent executing the whole transaction. Furthermore, site and link failures cannot be frequent or long-duration events in a well-designed and well-managed distributed system. So the probability of the failure of a coordinator happening after it sent prepares thereby blocking the subordinates that vote yes in the prepared state until its recovery is going to be very low. Now let's look at how the authors implemented this commit protocols in System RSTAR. System RSTAR is an extension or an evolution of System R, which is a centralized database management system. And each site has one transaction manager and has one or more database managers. And each of these have their own log files. Now, the transaction manager is a new component as of the paper's writing, and its function is to manage the commit protocol, perform local and global deadlock detection, and assign transaction IDs to new transactions originating at that site. So in that sense, transaction managers are the non-leaf node of a process, and it writes only commit protocol related records, while database managers are the leaf nodes of the process, which writes undo or redo records and commit protocol related records. When different processes communicate with each other during the execution of a commit protocol, it is actually that the transaction manager incarnations that communicate with each other and not the database managers incarnations. In cases where the transaction manager and database managers at a given site make use of the same log file for inserting log information of all transactions at that site, the records are inserted in order to avoid some asynchronous log writes. In this case, the former does not have to force write its collecting record, since the force of the collecting or prepared record by a subordinate will force it out. Now, if we assume the processes of a transaction communicate with each other using virtual circuits, and that new subordinate processes may be created even at the time of receipt of a prepare message by a process, then it seems reasonable to use the tree structure to send the commit protocol related messages also. So this approach avoids the need to set up any new communication channels just for use by the commit protocol. Furthermore, there is no need to make one process in each site become responsible for dealing with commit-related messages for different transactions, just as it's implemented in Encompass. Just as RSTAR database managers take checkpoints periodically to bound the database manager restart recovery time, the RSTAR transaction manager also takes its own checkpoints. The transaction manager's checkpoint records contain the list of active processes that are currently executing the commit protocol and those processes that are in recovery. We note that we do not have to include those transactions that have not yet started executing the commit protocol. So the transaction manager checkpoints are taken without completely stopping all the transaction manager activity, in contrast with what happens in RSTAR database manager. So the transaction manager checkpoints are taken without completely stopping all transaction manager activity. So during a site restart recovery, the last transaction manager checkpoint record is read by a recovery process, and a transaction table is initialized with its contents. Then the transaction manager log is scanned forward, and as necessary, new entries are added to the transaction table or existing entries are modified or deleted. Unlike in the case of the database manager log, there is no need to examine the portion of the transaction manager log before the last checkpoint. The time of the next transaction manager checkpoint depends on the number of transactions initiated since the last checkpoint, the amount of log consumed since the last checkpoint, and the amount of space still available in the circular log file on disk. Now, System RSTAR supports transaction serializability. It uses distributed two-phase locking protocol. Since many processes of a transaction might be concurrently active in one or more sites, more than one lock request might be made concurrently by a transaction. It is still the case that each process of a transaction will be requesting only one lock at a time. A process might wait for one of two reasons, either to obtain a lock or to receive a message from a cohort process of the same transaction. In this scenario, deadlocks, including distributed or global ones, are a real possibility. So in system RSTAR, it allows deadlocks to occur, and then it just resolves them by deadlock detection and victim transaction abort. In system RSTAR, there is one deadlock detector at each site, and each deadlock detector operates asynchronously. The frequencies at which local and global deadlock detection searches are initiated can vary from site to site. Each deadlock detector wakes up periodically and looks for deadlocks after gathering the wait for information from the local database managers and the communication manager. If the deadlock detector is looking for multi-site deadlocks during a detection phase, then any information about potential global or multi-site deadlock cycles received earlier from other sites is combined with the local information. No information gathered or generated during deadlock detection phase is retained for use during a subsequent detection phase in the same deadlock detector. Information received from a remote deadlock detector is consumed by the recipient at the most during one deadlock detection phase. This is necessary in order to make sure that false information sent by a remote deadlock detector, which during many subsequent deadlock detection phases may not have anything to send, is not consumed repeatedly by a deadlock detector, resulting in the repeated detection of false deadlocks. If, due to the different deadlock detection frequency of the different deadlock detectors, information is received from multiple phases of a particular remote deadlock detector before it is consumed by the recipient, then only that remote deadlock detector's last phase information is retained for consumption by the recipient. This is because the latest information is the best information. Now, once a global deadlock is detected, the interesting question is how to choose a victim. And the general algorithm here is that in the event of a global deadlock, it makes sense to choose as the victim a transaction that is local to the site of detection of that deadlock, assuming that such a local transaction exists, or the youngest transaction, which may be a non-local transaction. That is everything about the paper by Mohan and his coordinates. Thank you for listening and have a great day.